I'd like to thank you all for coming. I hope you've all been having a great ELC. I know this is the last talk on the last day, so I promise you this talk is probably not going to go over time or anything like that. I'll try to keep things short and sweet, and we can talk about whatever you want towards the end here. So a little bit about who I am. My name is Scott Garman. I work at Intel's Open Source Technology Center. I've been working on the Yocto project as a software engineer for the last, I guess I started about 3.5 years ago there. And then more recently, this MinoBoard project has come out. The MinoBoard is one of the first open hardware platforms that has an Intel Atom processor on it. And I'm acting basically as a technical evangelist for the MinoBoard. So I'm going to talk a little bit about the MinoBoard because that's kind of what drives this, this demo here and one of the reasons that I've been doing it. And then in other areas, I live in Portland, Oregon in the US. And Portland's known for being a very kind of bike culture kind of city in the US, which maybe to folks in Europe is not quite a big deal, but it is nice to live in a city in the US that is fairly friendly to bicycling and getting around, transportation by bike. So I'm kind of in the maker thing. I have a background that I started off in college as an electrical engineering major and then switched over to computer science actually when I discovered Linux and the open source movement. Really kind of motivated me, but I do have a little bit of a background in EE, and I still like playing around with things, soldering stuff up, breadboarding little prototypes, and hacking robot kits. So another thing people who know me will tell you is that I have a slight obsession that some of us in the geek community have with puns. And so, especially when it comes to fish puns, if you can think of any good ones, be sure to let me know. That works well, given that most, this is at least in the UK. I wouldn't necessarily try that if I was giving the talk in Asia someplace, because the translation doesn't always come through. So this isn't going to be a big sales pitch about the MinoBoard, but I do want to tell people about what it is, make sure there's some awareness about it, because again, this is one of the motivations behind doing this project. So the MinoBoard was basically designed as a platform for the Yocto project, as a matter of fact. We wanted an open hardware and a fairly affordable platform that people could use for Yocto project development. Being from Intel, we wanted it to be based on the Intel Atom processor. And we worked with a third-party company, CircuitCo, which many of you may know is the manufacturer of the BeagleBoard and the BeagleBone, and some of those other kind of successful community-oriented boards. So we saw a good fit working with them to develop this kind of board, which is kind of like our version of that. We want the MinoBoard to be kind of a successful community board with a healthy open source community. And one of my roles as technical evangelist is to try to kind of develop that community, to kind of foster it and get people excited about this. So the MinoBoard was designed, we like to say, with performance, flexibility, openness, and standards in mind. And so like I said, it's the first open hardware Atom platform. And it's a pretty exciting time to be at Intel now because the whole concept of open hardware and having the schematics, the design files, and everything available for embedded system boards is something that I finally see as being embraced. Some of you may have heard about the announcement of Galileo, which is a new kind of like an Arduino on steroids. It's got the new Quark processor in it. And that is also going to be an open hardware platform. You'll be able to get all the design files available for that. So I'm seeing a little bit of a paradigm shift within Intel and embracing these things, and I think that's a great thing, and it's something I'm pretty excited to be a part of. Spec-wise, the MinoBoard has a gigahertz CPU. It's based on the Tunnel Creek processor. It has a gigabyte of RAM. It is a single core system, but it has hyper-threading, so for some multi-threaded applications, it'll act as if it's a 2-core system. And one of the things that's unique about the MinoBoard is it's got really strong I/O performance. So we've got PCI Express on this board that gives us good I/O capabilities. So we've got SATA on it. We've got full gigabit Ethernet as opposed to tying a 10100 NIC to a USB line. We've tried to make this board kind of straddle some different markets. I think it's going to be very popular in the professional kind of like embedded product development market because of that open hardware nature of it and the fact that it's one of the more affordable Atom platforms that you can get today. But we also did some things with the MinoBoard, like adding some GPIO buttons and LEDs and things so that you could take the thing right out of the box and immediately start working on it, hacking on it, and interacting with it. And it has a kind of an expansion capability so that you can add on these, we call them MinoBoard lures, which are these add-on expansion boards to add other capabilities to it too. So we like to say that the board is friendly to hobbyists. It's not as cheap as some of the other options out there, but it's friendly to hobbyists, but it also scales up to kind of more serious embedded workloads. And I see a role for this board in areas where you need additional processing performance, you need that I/O throughput capability. And there are many people who are getting into embedded development nowadays. It's becoming more and more common. It used to be kind of like a niche thing that people were doing. I feel like other platforms like the Raspberry Pi have really enabled more people to get into this embedded community, and people are going to want to have plenty of options. So this is one of those options that fits into that. The Minnow board has various embedded I/O. So if you're used to things like SPI bus, I2C, GPIO lines, and even controller area network support is on the Minnow board. The board is 10.7 centimeters square. The MSRP is $189 US. If you want to buy it in Europe, our two main distributors in Europe are Farnell and Teigl, which I think is based in Austria. And we ship it with the Angstrom Linux distribution, which some of you may be familiar with. The nice thing about Angstrom is that it's a binary distribution. You can install binary packages using a package manager online and everything. But it's also a distro that's Yocto project compatible, and that helps us to continue our message with getting people involved, potentially in using the Yocto project on this as well. So that's my little pitch about the Minnow board. You can learn more at our website, minnowboard.org. And I heard some rumors that there might be some Minnow boards that would be available at the last session of the day. So you might want to show up at the last session. I think there are going to be a few of them given away. There's going to be a little contest. So let's talk about the robot arm itself. So this project is the Minnow board. I call it the Minnow board fish picker-upper. And the purpose of this project was I wanted to create a demo that uses the Minnow board and does something that's kind of fun and kind of like maker-oriented type of thing. And I wanted to specifically take a technology that a lot of people find intimidating, which in this case is computer vision and object detection, and see how simple I could make it. See if I could make it into a project that a family could do with their kids over the course of a weekend. And I wanted to make it as affordable as possible. I wanted the robot arm, I wanted to keep that as cheap as possible, and that ended up driving some compromises I had to make. This robot arm doesn't have any servo motors in it, for example. And I wanted to specifically make use of OpenCV because it's a pretty well-known computer vision library. So the way this works, you can see the robot arm right here. And what I've done is this is the OWI robot arm. You can buy it on Amazon, at least in the States. And it is a very affordable robot arm. Oh, look at that. I think it's around $40 or $50, and it's a kit, so you can put it together. You can see how the motors and everything are set up in it. And for another $20 or $25, you can buy a little USB control module, so you can control it via basically a USB serial to kind of interface. I think by default it comes with a joystick control, but if you want to do computer automated control over it, you want that additional board for it too. The next thing I did was I took just a standard Logitech USB web camera and I mounted it to the base of the robot. So this thing is kind of looking out as the robot kind of rotates around, and we're going to make use of that. And I wanted to basically have this robot arm pick up a small object. I have a nice spongy foam, I call it a foam fish. It's kind of in the shape of a fish. I didn't bring it with me. And it can identify this object, pick it up, and then move it over to like a dinner plate or something like that. So that's the summary of the Minnow board fish picker-upper. So there were some challenges with the approach that I initially wanted to take with it. At first I was being a little bit more ambitious. I wanted to mount the web camera to the top of the robot arm so I could try to maybe get some three-dimensional control and have it kind of zero in on the object it's trying to pick up. But there were a couple of challenges with that. One of them is that the field of view on the camera wasn't that great. And the other is just that because it's such a cheap robot arm, I think the heaviness, the weight of the camera itself is pretty strong. So you'd have to go to something more specialty, like a little mini camera or something like that on there if you wanted to give that a try. And that would have added more expense and complexity to it. So rather than putting the camera on the kind of jaws up here, I said, okay, let's try to constrain things a little bit more. What we'll do is we'll just put the camera down here on the base, and we'll just use the computer vision to control the one degree of freedom, the kind of the rotation of the base as it zeroes in, and then the reaching down and the picking up of the fish object would have to be like a canned routine. The other thing is the lack of servo motors here. Can anybody tell me what the difference is between just a plain DC motor and a servo motor? Yes?
Oh, yeah, well, servo, well, it's basically a stepper motor.
Mhm.
Really easy to say that, for example, two equals as they.
Right, exactly. So you get some feedback from servo motors. You can figure out where it is in its range of motion. And this robot arm does not have servo motors, it just has a plain DC motor. So when I'm controlling it, I'm basically issuing commands to say, rotate this motor in this direction for, and you know, sleep for a second or something like that, and then you know, wake it up and stop it. So that, what that means is that I can't figure out really if there's, if the motor, if the arm is moving in one direction, it's hit its limits, and it's kind of like, you know, grinding through the motor. So you have to be careful to do that. So I try to model that in software. I say, I know I have so many seconds of range of motion, but it's not even that simple, because then you get into the situation where if I make a number of movements in one direction and then back, it's not, the steps that it's going through, it doesn't put you back into the exact same situation if you're moving back and forth. So there's some slop in those motors too. So that provided some challenges I had to deal with as well. The other thing is I ended up using OpenCV's HAR wavelet-based object detection, and that is not an exact science. There are some difficulties, especially if there are different lighting conditions that the robot is in. I will get either more or less accurate object detection, and sometimes I'll have to tweak some of the parameters to get that to work just right. So plenty of challenges involved in this, and I tried to do the best I can to work around them. One of those challenges, too, that I didn't mention was the fact that this base has a bunch of D-cell batteries in it. And I also knew that I didn't want to run this off of batteries, because the motion, again, would be dependent on how healthy the batteries are. So one of the first things I did was I modified the base. I drilled some holes in it, and I'm making use of some power supplies. And unfortunately, these power supplies are not very friendly, even using a power converter with the power outlets out here, and I found that I couldn't get this working. Otherwise, this would have been in the Yocto project booth over the last couple of days. But basically, so you know, I have a couple of 3-volt power supplies that are powering this, and this allows the robot arm to work consistently given that power source. This here is a close-up of the robot's base where I've got the web camera mounted. I basically just took some double-sided tape and taped it down. It's pretty securely attached to the base. And so that summarizes some of the modifications I made to the actual robot, OWI robot kit itself. So OpenCV, how many people in here have worked with OpenCV before? Okay, so a number of you, it sounds like most of you though are probably new to it. So basically what OpenCV is, it's the most popular computer vision library you can get that's open source. It's a BSD licensed library. It actually was started by Intel in 1999, although I believe it's maintained currently by a different organization. And there's a lot to it. So there's a lot more than just object detection in OpenCV. There are something like 2,500 algorithms that can do all sorts of things: motion tracking, complex image processing, taking the negative of images, filtering things out by color, all sorts of stuff you can do with OpenCV. And it's a cross-platform library, so you can work with it in a number of languages like C, C++, Python, Java, I think even Lisp. I'm not sure about that, but I think I read about that too. So the object detection system, basically, how does it work? How do we train a computer to recognize an object? So OpenCV has a couple of different algorithms you can use to do this object detection, but I'm using what's called HAR classifiers. And the way it works is basically we feed this computer learning program a set of images that include the object that we're trying to detect. And those are our positive images. And then we have a bunch of basically false negative images, or images that don't have the object that we're trying to detect. We feed it into this kind of machine learning algorithm. And it basically gets trained, it learns to identify what are the similarities between a lot of these pictures that have the object we're trying to detect, and make sure that it's not giving false positives in the pictures that it knows doesn't have the object. And it does this through this HAR classifier system. And the nice thing about HAR classifiers is that they're computationally efficient. And what they do, I'm probably not going to explain it very well. I do have a little YouTube video that I can show you that kind of goes into a little bit more detail. But in a overgeneralized way, HAR classifiers are a series of tests that you make against a picture that you're trying to figure out if it has an object in it. And the first initial test you run, you do it in a series, will give you very accurate information if it knows for certain the object is not in the picture. And so if you run these computationally efficient classifier levels, you can immediately kind of rule out certain images if it doesn't have it. But if it thinks, okay, it might have it in it, then you go on to the next kind of more computationally intensive test to determine if the object is in the image. And then it keeps going down the chain until it gets to the more seriously computationally intensive ones that give you a much more accurate view of whether that object exists there. So to train a HAR classifier, you have to start with fairly large sets, and it's recommended that 100 or more images of the object that you're trying to detect to make sure that there's plenty of data for it to work with. And in addition, it's unfortunately it's not as simple as just taking the photo and feeding it into this machine learning algorithm. You have to help it out a little bit. You have to mark out with a box this region of interest that shows where that object is within those pictures. And there's a utility for doing this to help you out doing this called Object Marker, and I'll give you a quick demo of that, and that will I'll give you an idea of the process that you have to go through. And then there are a couple of commands that you go through that basically take the output from Object Marker, which is like a vector file, and then you feed it into this OpenCV HAR training program, which is actually what does the machine learning. So this is just going to be a quick demo of what I've got here. So let me bring over a terminal screen. Okay. And so what I'm going to run here is that object marker program, and I'm going to generate this vector type file, positive description.txt, with a directory that I have, in this case, just a handful of images that have the object in it. So what you see is this is the foam fish object I'm referring to. So you go, you draw a box around it, you try to make it as accurate as possible, and you move on. And what you're trying to do is you're taking photos, especially of the object in different contexts, different backgrounds, so that you can get as much information about this as possible. So you might say, take the object and put it on your spouse's head, or like in low contrast types of backgrounds, and so on and so forth on the barbecue grill. It was lots of fun walking around and taking this little fish thing and trying to take photos of it everywhere. And if you are doing things that are more common, such as trying to do facial recognition, which is a really popular thing to do with OpenCV, there are pre-created databases of information of this HAR classification that you can make use of. You have to go through this effort generally if you're trying to identify an object that that doesn't have such a wide audience of people making use of it. So if we take a look now on positive descriptions, you'll see that we have basically these are vector files that describe where in that image the coordinates of the rectangle that we created, and that can be fed into later steps along the way. And then as far as the explanation of HAR, that there's a guy on YouTube who did a much better job at it than I did. So let me put this right here. It's not quite big enough to... Hold on. There we go. And let's see if I can grab the microphone and actually you can hear the audio from this.
In order to conduct face detection, we chose HAR object detection as opposed to other methods like SIPs due to its reliability and speed. HAR object detection acts as a funnel, where in every region of an image image is analyzed using a set of classifiers called HAR features that act as a funnel called a HAR cascade. The classifiers at the top of the cascade are extremely fast and have extremely low false negative rates to immediately remove regions of an image that do not contain a face. The HAR features become more and more complex further down the cascade as an optimization. Images are rejected as soon as possible if their features do not resemble a face. The HAR object detector works by calculating an integral image of a grayscale image. Similar to an integral of a function in calculus, every pixel of an integral image contains the sum of the intensities of every pixel above it and to its left in the original image, allowing the average intensity of any rectangular portion of an image to be obtained by accessing only 4 pixel values rather than hundreds at a time. A HAR object detector takes advantage of 3 different types of rectangular features: edges, lines, and combinations of 4 rectangles in order to detect a single object. A HAR object detector defines thousands of these rectangular features in different regions and combines these features in order to define an object and detect it efficiently. Each of these features is recognized extremely quickly in an integral image. Since thousands of features are verified thousands of times for every single frame of video, the integral image of the frame allows the software to be much more efficient by effectively calculating the image's intensities in advance. For face detection specifically, we used an XML file containing a cascade with thousands of rectangular features that are present in the face. For example, the cascade contained definitions for the cheeks being brighter than the eye socket, the nose being brighter than the eye socket, and the forehead being one of the brightest portions of the face overall. Thousands of these comparisons are conducted in real time to ensure that a single region of a single frame of video contains a face.
So I don't know if the audio came through too well on that or not, but I felt like he gave a much better explanation than I could have at this point. So I'd like to thank Varun Ramesh for that video. And that gives you a little education on HAR object detection. Okay, well actually, why don't I give you a demo? Like I said, I didn't have the robot arm working here, and I apologize for that. I do have a video I can show you, though, of the robot actually working. So this is in a hotel room earlier this year. So I've got this kind of blue placemat background down, which is kind of like the back of an aquarium, aquarium wallpaper. So that's kind of water, and that's the fish in the water. And I've got the MinoBoard set up there, and we're running it's kind of hard to see, the MinoBoard fish picker upper code, which is on GitHub. I'll share a link with that at the end. And you see the robot arm is looking for it. In that red box around the fish object is OpenCV's object detection saying, okay, we've detected this object. And it'll zero in on it using smaller movements and then reach down and try to pick it up. And then it goes and drops it off in the plate there, or the bowl. So again, it's in one sense it's a really simple thing, but like a kid learning how to do this. I mean, kids love robots to begin with. To be able to control them and give them like autonomous, capabilities such as this is pretty exciting. So that was the goal of the project, is to try to enable this kind of excitement that you can get around autonomously controlled robots that can see. So there you go. All right, let's see if I can start the slideshow at the right slide. Yes, okay. So OpenCV obviously isn't the only way that you can do computer vision. And I just wanted to mention briefly that there are other methods. So I talked a little bit about the fact that using the OpenCV with the web camera can be a little bit sensitive to lighting conditions. One of the alternatives you could use is something like a Microsoft Kinect, which actually uses infrared to do its vision control. And the infrared is the amount of light in the room is irrelevant to that. And one example of a robot that you can make use of is something called the TurtleBot, which is made of pretty commodity parts as well. So it actually uses a kind of a Roomba as its base. They actually sell Roombas that don't actually vacuum, but are just can be used as kind of robot experimenter kits. And then it's got the Microsoft Kinect up there as its computer vision. And so it's got a whole platform. It uses, I think, the robot operating system that you can make use of to control this. And you could put either like a netbook or a Minnow board or some little embedded board in there to actually control it. So that's an alternative thing here. So one of the other purposes of this project was to use it for advocacy of the Octo project. And so while you can use the Angstrom distribution and you can install OpenCV and the dependencies that this thing requires, I wanted to briefly go over to how you would enable this kind of application using the Octo project. So basically you needed to grab the Yocto project release and its metadata there, and you'll find that you don't have certain programs that you need. So for example, OpenCV, and OpenCV has a number of dependencies such as libav. If you're using the web camera, you want video for Linux utilities and so on. But if you look around, when you're in this situation with the OE core layer, you don't have the software you need. You don't necessarily have to jump in and start writing your own recipes yourself. So it turns out that the Meta Open Embedded repository had just about all the recipes that we needed. We were able to grab the recipes from there and create our own layer based on that. So the layer name I gave it this was Meta Robot OpenCV Demo. And I created an image recipe that basically just booted up to X and gave me a terminal window, and that included all the required OpenCV stuff. And there's a website you can go to, I believe it's layers.openembedded.org, which is a searchable index of all the different layers you can get for open embedded, Yocto project layers basically. And so you can enter in the name of a recipe that you're looking for, and it will return, where you can find that. So that's a really handy tool to use when you're trying to grab some of these other recipes. So what is a Yocto project? What is an OE layer? Basically, it has a directory structure here where you need a configuration file. This is your layer.conf file. And that will tell the BitBake tool where you can find the remaining recipes in your layer. That's kind of like a boilerplate that you would make use of. And then you have a recipes subdirectory, and then you have the different applications that you need into it. And you would put the recipe for SWIG or recipes for SWIG within the SWIG directory, and enable that in your build bblayers.conf file. You would point to both your OE core base layer and then this layer and then the BSP layer for the machine that you're building for, etc. And to show you what an image recipe looks like in Open Embedded, we have this robot OpenCV demo image, .bb, and it's pretty basic. We've got a description. We have something called image features. And so, what's going to bring in most of this is X11 base will bring in all the sub-dependencies you need to get a working Xorg-based system. And I just added a couple other things, splash screen, the Dropair SSH server, and so on. Then we append here in image install. We can add the additional specific packages that we want to have for this. So OpenCV apps. There was a calibration utility that I use for manually controlling the robot arm that uses WX Python, so I wanted to include that as well. I think I threw Mesa demos in there just to do some benchmarking, and so that's an example of how quickly you can write an image recipe for the Octo project. So I've been working on this. I think I got this first working for Linux Fest Northwest in April of this year. And I've been kind of developing it and adding more to it as time went on. And there are some other things I'd still love to do with this. The code for this is basically a big state machine, but I'm not using any Python state machine libraries. So it'd probably make the code a little bit more maintainable if I migrated over to a Python state machine library. One of the ways you could improve the reliability of the system would also be to increase the number of samples that are used for the OpenCV training. One thing I've been wanting to do too, so the Minnow board has a number of GPIO headers that you can connect to, and I thought it'd be really cool to have it detect a fish by color, so that you could have some push button switches attached to it, and you could pick whether you want it to pick up the green fish or the blue fish or the yellow fish, and then have the program be able to do that. And then, like I said, the control of it via some of the GPIO buttons. Some resources I've got here. So information about the Minnow board, the Octo project. This is a link to the actual specific model of that robot arm you can get. Some stuff about OpenCV, a link to that video that we watched. And most importantly, if you want to actually take a look at the code that's running this, as well as the Yocto project layers that you make use of, you go to github.com/minnowboard. We have our own organization. You'll find some repositories for that stuff too. So really, I mean, that was what, half an hour worth of speaking here. I'm happy to answer any questions people may have about this kind of thing. Yes?
You didn't recognize the bowl on the way back, you just knew where it was.
True. Yeah, that would be something else you could do. You could add some more object detection capabilities with recognizing the bowl. And then you could have the bowl in arbitrary locations. Yep.
And what about the distance with fish? It should be the same distance, or we take the distance of fish?
Yeah, it's because it's just two-dimensional, and again, because I'm only using that one axis of rotation, what I did was, you couldn't see it on the blue placemat, but I just had a couple of dots set out that were a 6-inch radius from the base. So as long as it's along that 6-inch radius, it should be able to pick it up. Yeah.
What is the CPU utilization of the board running the demo?
So it depends on how fast you want the frame rate to be. It turns out one of the things that's the most computationally intensive with this is actually just getting the frames from the web camera itself. I think I settled on about 5 frames per second I wanted to get. And by contrast, so I tried running this on a Raspberry Pi, and it was really choppy. It was actually barely usable at that point. So you'll see some performance differences between Minnow and some of the other platforms, and that we're making use of definitely the CPU. But the actual OpenCV detection wasn't especially high. I might have only been using 40 or 50% of the CPU for that aspect of it. And if you do want to replicate this on another board, in the code I include some comments that identify the parts where you can slow down the frame rate to make it more usable for lower performing options. Yep. Back there first.
Can you do filters in OpenCV where you could just chop it down to maybe just one color? So
Yes.
that you could identify quicker?
Yeah, that would actually probably be a more reliable way and a simpler way of doing this. And the reason I didn't do that, it was, again, because I wanted to get into this whole concept of teaching people to use something complicated like object detection. And because of the object detection, too, you can even bring in the whole idea of like you're using artificial intelligence and machine learning algorithm to get this to work. So that was part of the story behind this, but that would be another way that you could go about doing this, certainly. Yes, there's a question here.
Just curious, you use Python for most of the implementation.
Yes.
And
it's not-
OpenCV library internally. How's that structured? What is used over there to actually implement functionality?
So it's pretty simple. Like the script that's really controlling this is I think around only 400 lines of Python itself. So what you do is you use OpenCV to open up the web camera device that you're making use of. You're pulling frames from it, and then you run code that analyzes those frames using the HAR detection method, which you're pointing at the database that you generated through those steps that I talked about, where you define the region of interest, and then you run that OpenCV HAR training command. And what that outputs is kind of a directory structure that acts as a database of sorts. So you need to be pulling in images and then pointing the Python code to that database. So.
What does the OpenCV give to you? Does it give you an offset where to move?
Right, and then what it does is when it identifies the object, you can get a function that returns, and what it returns is the coordinates of the box that it's drawing around it, and then I have to figure out what is the center within that box.
Where it is in respect of the full view of the
Right.
camera.
Yep, exactly.
On the left and the right.
Yep.
Well, it's more the feedback of the motors.
Mhm.
Sort of starting using the camera for getting feedback from the artists.
That would probably be, might be possible in some ways. There's some things you could do that would make it easier. If you had a camera that was looking at the robot arm, there are these hatch patterns. There's a name for them, and I forget what it is, that you can use that are actually really easy to identify with OpenCV. And you can put those on the axes that are rotating. And so you could do things like, figure out what the degree of rotation is, making use of OpenCV again. But it would have to be kind of like a third-party view of it, not necessarily something that is got a first-person view out of it, I guess. So.
Maybe it can be done using a pattern on floor.
Maybe, yeah.
Of course, they simplify also the contrast.
Mm-hmm.
Helps to
Sure. Yeah. Yes.
And this web camera, what kind of image format does it use? Is it JPEG or it's YUV?
Oh, I think it's I think it's just a kind of a motion JPEG where I'm pulling the frames out of.
So you have to decode it.
Yeah.
Okay.
Yeah, something that might have H.264 encoding built into it might be more efficient too. Yep. Anything else? All right. Well, like I said, last session of the day. Definitely show up to the closing session, and thank you all for coming. Appreciate it.